All right, now we're going to work with the tail to tip method in vectors that are in 2 dimensions. Okay, so let's just say we have a vector that is, and I'm going to use something other than displacement since I've already been using that one so much, and I'll do it in a more advanced problem later. Let's use velocity. So let's say that a plane is flying or a car is driving, say 35 meters per second in this direction, and we'll say that it's at an angle of, I don't know, that looks like maybe 40 degrees above the positive x-axis or north of east, right? And then let's say that car turns directly east and travels at 20 meters per second. Then I want to know, well, what is the actual resultant velocity? Okay, so if it turns to the right, or it goes east at 20 meters per second, and notice that I've done my tail to tip. So I have my first vector, which is here, and then I put my second vector at the tail of the first all the way to the tip of the last. And I want to actually know what is the resultant velocity. So remember that the resultant is going to be from the tail of the first to the tip of the last. So my resultant would actually be this. Right? So this is my resultant vector. And I want to know what the magnitude is and the direction. So the magnitude is the length of the vector, and the direction would be described by the angle, right? So in order to do this, I need to use my components in order to figure it out. So the 35 meters per second is going to have both an x and a y component. So like this, and then like this, right? And then my 20 meters per second really only has one component to the right. Okay, so vector 1 has an x component, vector 2 has, or sorry, vector 1 also has a y component, and they're both positive, you can see to the right and to up. And then my second vector only has a component to the right. But if we notice, we could see that the amount of x that is a part of the first vector, as well as if I wanted to move the red one down here, would be here, is actually equal to the resultant x component, where this would be the x of my resultant vector here. So in other words, we would say v1x plus v2x is equal to vector resultant x. Then if we looked at the y's, same thing applies. So if we look, we see that the blue has a y component, the red does not. So all of the y's that are there actually add up to be the y of my resultant vector, right? So in this case, I would have just v2y, or sorry, v1y, since the other one is 0, is equal to my resultant vector, y component. And then once I had those two sides here, this one and this one, I would be able to very easily figure out, using trigonometry and the Pythagorean theorem, the length of my resultant vector and the angle. So let's just go ahead and do that. So in order to find the x and the y component here, you can see that I'm going to have to use cosine here. So it would be, and let me just write it all out, the cosine of 40 is equal to, and that would be adjacent over 35, my hypotenuse. So the cosine of 40 times 35, and I get 26.8. Alright, so 26.8 is my vector to the right. And then to figure out my y component, in this case, then I would use the sine of 40 is equal to the opposite over 35. So the sine of 40 times 35. And I get 22.49. So 22.49 up. Right? And so then I could figure out my resultant x and my resultant y, right? So x, the 1x, which is 26.8, plus my vector 2's x component, which is just 20. So this resultant would be over to the right 46.8, and that's meters per second. And then this would be up 22.49 meters per second. So I have this side, and let me just draw it more distinctly so you can see it. So this side here, I have just calculated to be 46.8, and then this side here, I had calculated to be 22.49. So let me just pull that away because it's sort of getting messy now. I want to just draw, this is, sorry, I changed the angle a little bit, but this is my resultant, which I'm trying to find, and I know that this side of my right triangle is 46.8, and this side of my right triangle is 22.49. So now, just very simply, I have to figure out this side, which is just using my Pythagorean theorem. So I'm going to do 46.8 squared plus 22.49 squared, and that gives me, oh, take the square root, 51.92. So that would be meters per second. So that would be the magnitude of my resultant vector. But I also want to figure out this angle or describe the angle somehow. And so I'm going to choose that one. And now that I have my hypotenuse, I could really use any trig function, but let's just use tangent. So I would say the tangent of that angle is equal to opposite 22.49 over 46.8. So 22.49 divided by 46.8, and I get this decimal. In order to figure out what the angle is, I'm going to do second tangent of my answer, and I get 25.7 degrees. Right? So the actual resultant would be 41.92 meters per second, and that would be 25.7 degrees above the positive x-axis, or I could say north of east. Okay? So let's just kind of review what we need to do here in order to solve for or to perform what is called vector addition for something that is in 2 dimensions. So we start by using our tail to tip method, placing our vectors tail to tip, and then placing our resultant vector at the tip of the first and pointing it towards the tail of the last. Then I determine the x and y components using trigonometry for every single one of my vectors. I add the x's and the y's together to find the resultant x and the resultant y. And then I use Pythagorean theorem and trigonometry to figure out the hypotenuse as well as the angle. Alright, in the next video I will actually do a 3-vector problem, which is a little bit more complicated, but will give you a little bit more practice or review of using this tail to tip method.